So in this slide, I'm going to talk about how you can master the 3D web environment. It is a visual blueprint for modeling, texturing, and optimizing interactive 3.js portfolios. You have a vertex data, you have a polygon mesh, you have a flat sequencing, you have a base geometry, untextured res, UV wrap review, you have a JS codebox. So the four pillars of interactive 3D web design. The first is the foundation, which is topology, establishing a mathematical edge flow. Mesh structure is a clean quad-based optimization geometry definition. You have a form modifier, which is like a procedural geometry manipulation. Operators are Boolean, subdivisional extrusion. Dynamic flow is a non-destructive addition. You have a surface texturing, applying color, roughness, and a mathematically generated patterns. You have a map types, which is diffuse, normal, roughness, metallic. You have a procedural set, which is like a math-based pattern. You have a delivery web of optimization, preparing the scene for the 3.js rendering engine. You have a GLTP, GLP export, efficient binary format. You have a browser integration, WebGL3, JS scene loader. Now clean geometry detects shading and a web and quads. Vertex count is for mathematical efficiency, highly optimized for 3D software algorithm. Deformation quality, smooth and a predictable. Vertex industry standard, TRIS. Vertex count 3, mathematical efficiency, basics, limit, advanced edge loops. Deformation quality rigid. Vector vertex is used sparsely. N-guns. Vertex count 5 plus, mathematical efficiency, causes calculation error and shading artifacts. Deformation quality, unpredictable, pinching, vertex avoidantly. 3D software calculates lighting and geometry updates continuously, uniform quad topology, and so these calculations run smoothly, especially when passed to a browser WebGL render. Sculpting based forms through addition and subtraction. Extrude E pulls a face output to create a non-volume vertex count non-replica operation. Addition. Insert I draws a concentric smaller face inside an existing one. Vertex count non-application operation. Subtraction. Loop cuts. Control plus R slice the geometry along a continuous ring. Snapping aligns specific vertices to exactly match target objects. The modifier stacks automate repetitive geometry. Solidify adds mathematical perfect thickness to the flat planes. You have a mirror save 50% of the work by duplicating geometry across an axis. So these are the modifiers. You have a modifier, solidify, mirror, array, subdivision, surface. Then you have an array, procedurally clone objects along specific mathematical offsets. Subdivision, surface, smooth blocks geometry into organic curves or dividing faces exponentially. Bending rigid mapped into an organic shape. Bezier curves. Curves act as a skeleton by increasing the depth parameter, and a single mathematical line instantly generates a tabular 3D map. Perfect for PC water tubes and flower stem. Simple deform modifier. Apply the universal twist, bend or tap to an entire joint mesh, turning rigidly straight leaves into a naturally hanging vines. The three paradigm of texturing method: base color principle, BSF, DP, step speed is fast, customizability high, memory footprint near zero, procedural node medium, infinity tiny, PVR slow, low, massive. Procedural materials are just math equation. You're not painting colors. You're passing a grayscale math gradient through a filter to selectively reveal the colors on a 3D surface. Texture coordinate. You have a mapping. You have a generates value 0 block to 1 white. You have a noise texture. Act as a filter mapping values to color ramp principle BSDF. Mixing texture through the vector formula 1 add 100010110. Adding color vector pushes the total value closer to 1. Creating an artificial brightened blown out mix formula to multiply 1001. Multiplying vector darkens the result. Multiplying pushes the value closer to 0, creating natural realistic shadows. Wrapping 2D images around 3D image. Step 1. The UV and ring analogy seems to act as a precise cut line, telling the software how to flatten a 3D image without stretching the geometry. Step 3. Once flattened, the UV maps act as a stainless over a high-res PVR to project the exact physical data back onto the 3D device. Illuminating the environment. HDR wraps the scene in a real-world 4K image, providing ultra-realistic soft bound shadows. Sky texture. Procedural sky algorithm that allows manual adjustment of sun elevation, rotation, and harsh shadow angles. Emission shaders, turning base geometry into an active light sources, perfect for creating stylized glowing backdrops in a dark mode scene. The pre-flight web export scale. Applied transform scale and transfer. Unapplied scale causes modifiers and 3.js physics to behave unpredictably. Apply modifier. Browser cannot compute real-time structural modifier. Meshes must be back into permanent destructive geometry. Delete hidden faces. Faces users will never see waste UV space and force the GPU to render invisible fiction. Before, then it goes after, before, after, before, after. Consolidating draw sales and origin. Wet for web. 51 draw call. Separate projects forces the GPU to process 51 individual rendering instructions per frame, destroying browser frameness. Optimized draw call. A unified mesh requires only a single rendering instruction, drastically improving performance. Origin point. Snap to the base. When a Java scales the object from 0 to 1, it grows naturally from the floor up, not from its center. From raw geometry to the browser ready. By mastering topology, procedural math, and a mesh, you elevate 3D modeling from static art into a performant interactive web web architecture, delivery, final baked scene, hardy lighting, immersive material, browser ready, flat colors, procedural structure, flat shading slash no lighting, uniform quad topology, optimized geometry. Thank you.